Swayam Prabha. Digital India. Educated India.
So now I'll handle a session on how to use Abacus to perform energy harvesting simulations. So Abacus, how many of you are aware of Abacus, like aware of the user interface? Okay. So just want to know, based on that I'll go from how basic I want to start the session from. So today we'll see two types of analysis. One is the modal analysis, another is a transient simulations. We'll fix a PCT patch to a cantilever beam and we'll give some basic citation and see how we can harvest the energy or read the electric potential out of the system. So this is the interface, Abacus interface. So any software has a set of modules. You just have to go by the modules step by step to finish your pre-processing, solving and your post-processing steps in your finite element simulations. So here in Abacus, the modules are given here. Okay, first I'll just go through the steps. So the first thing is, the left hand side you have the model tree. This is the model tree where you will be creating your cases, and in every model you will be creating your part and you will be assigning the material and the geometric properties to it. So the same set of options are present here also. It will be easy to follow over here. So first we'll create the part, then we'll assign the geometric and material properties. Then if it is a multi-component system, then we have to assemble the system. So for assembling, we have to give proper interface conditions. For example, in a cantilever beam with a PCT patch, we are going to bond the patch to the cantilever beam. So there are ideal conditions for that we will be giving. Then in this step, we will be choosing what kind of solver we are going to use to solve the simulations. Then in interaction, if there is any contacts or even the bonding conditions, that will be provided in the interaction. In load, we will be giving the loading and the boundary conditions, the most important part of your simulation. Any mistake can happen here. So we have to be very clear with, and we have to recheck whatever we do in this module. So then it is the meshing module. So where you will mesh, discretize your CAD model into elements, finite elements. So up to this we call the pre-processing part of your finite element model. Then we'll create a job, which means all the set of conditions that we have defined will be written in a file, and that file will be submitted to your solver and your solver solves the problem. And finally is the post-processing, where you visualize the results. So we'll start with a simple model. So the overall idea is, first we'll see how to use the graphical user interface, which is much easier. You can find many resources to do this. Additionally, we'll see how to use a text user interface, how to use a text interface, so that later you can conduct any parametric studies or optimization problems, or you can couple your Abacus to MATLAB or any of your Python codes so that you can do automating in your finite element code. Okay. So the first, I'm creating a part. So I call this the beam. So in Abacus, there is no place where you specify the units of your simulation. You have to consistently give the units. If you are following SI units, then everything has to be in SI units, because there is no place like in ANSYS or other software's console where you will select the unit measurements. So let me create a cantilever beam. So okay. So I'm having meters as my measurements. So 0.1 meters, which is 100 mm. And 10 mm width. So now I give the thickness to be around 2 mm. So next step, we'll do a simple modal analysis where we find the natural frequencies and the mode shapes. So it will give you a good feel of how the software flows, like how step by step how we work with the software. Then we'll go to the transient simulation. So now I have to create a material for it. So I create aluminum. So density will be in the general module, and then your elastic properties should be given here. 70 gigapascal. So first we have created a part, then we created a material. So then we have to assign that material to the part we have created. Okay. So the second option is called a section. Here we are going to create a solid section. So the material is selected as aluminum. Okay. So which is the one we created just now. We select that and click OK. So now the material, along with it we have created a section. So the section will be a collection of material properties that you have created. Now we are going to assign that section to the part you have created. So now we are going to assign the section. The third option is the assign section. So here in Abacus, we have to create something called sets. A set can be a collection of points, a collection of lines, a collection of surfaces, or a collection of cells, which are volumes. Okay. So a solid part over here, which is one complete part, we are going to assign the material or the section where the material is aluminum to this complete part. So we have to create a set that contains this volume. Okay. So just select the set. Can we name it? And we are assigning the section we have created to it. So the material is aluminum, the type is solid. These two information will be there in this section beam. So and that section we are assigning to the part we are creating. So once you have assigned a section, the color of the part turns green. So if it is not green in color, which means we have not assigned the section, which will throw an error later when you solve the problem. So far we have worked with the CAD and we have assigned a property for the CAD. Now there is something called an assembly module. In assembly module, we create a copy of the CAD. This is one way of doing it. We either create a copy of the CAD and you import it into this module, which means if there are multiple CAD or multiple parts, then you import all these parts into this assembly module and you assemble it here. So this assembly module has two options. So here we are creating an instance of your part, of your CAD. This assembly module has two options. The first option is called a dependent instance and the second option is called an independent instance. So the dependent instance means that your mesh is going to be dependent on the part, which means any modifications you do in your CAD will be reflected in your assembly. If you have 10 different instances of your same part, for example, you have a bolt that you model only once in your CAD and you're going to create 10 different instances of the bolt, copy 10 different instances so that it can be used in 10 different places in your assembly. So in this case, if you are selecting a certain type of mesh in your dependent instance, if you're selecting a certain type of mesh or you are partitioning the body so that you can which can help you with creating the mesh easily. So what happens is in dependent, there is only one type of mesh you can create because everything is linked to your source file, which is your CAD file. So you cannot have different types of meshes for the same CAD. So, but in an independent instance, there will be multiple copies of your CAD that will be created. So, every copy can be meshed differently. Okay. So, the downside of having a independent part is, independent instances, your memory requirements will increase. But in the downside of the dependent part is, you cannot have multiple types of meshes depending on where your bolt is used. So, I am creating an instance. So, the next is the step. The step is where you select the type of solver you need. So, there will always be a step called an initial step, where you will be applying any initial or boundary conditions to it, and after that you have to create subsequent steps. In every step you can conduct a different type of simulation. So these are terminologies that are specific to the software. In Abacus you call it the step. Okay. So here we are going to do something called frequency linear perturbation analysis, which is the modal analysis here. Okay. Here the solver is numerical solver that is used. So there are two types of solvers, eigensolver. One is a Lanczos solver and the subspace solver. AMS solver is also there, but the Lanczos and subspace are what we use for finite problems, that structural problems. So the Lanczos solver very well works for large systems where your degrees of freedom is very high. The subspace problems is more efficient for smaller systems where the degrees of freedom are less, but it does not solve coupled problems very well. If there is an acoustics plus vibration problem, then it might not solve it very well. There are certain assumptions that goes into the solver. So here we use the Lanczos solver, and we are going to request the first 10 eigenfrequencies. So we are going to do modal analysis, that we assign that the kind of analysis we do in the step module. Then we go for the interaction module. Here there is only one part, so there is no interaction between multiple parts. So we can skip this for now. And next is the load module. The load is where you give your boundary conditions and your loading conditions. The first option is the loading condition option. The second is the boundary condition option. We are going to do a free vibration analysis. So we'll just give a cantilever boundary condition. So we create a boundary condition. A displacement boundary condition. So again we have to create a set which will contain this surface, the fixed end. To this surface we constrain all the degrees of freedom. So next up we'll go into meshing the part. So here it says, so here on top we say this is in the assembly module. So since we have chosen the part to be dependent, the CAD has to be meshed, not the assembly. Once the CAD is meshed, every instance of the CAD that we use in the assembly will take up the same mesh. So we select the part of the same, select the CAD of the same part, then we mesh it. So first we need to seed it, which means we need to find the end nodes of an element, and then we connect it with its edges. So here we are taking an element size to be 1 mm. And then we mesh the part. So this is an automatic mesh, but we need the information of what the element we have used, what are the number of nodes in the element. So what kind of integration are we going to use, because we'll be using Gauss quadrature to numerically integrate to obtain the stiffness matrices. But what kind of, are we using reduced integration or full order integration? Those information can be obtained from this option, assign element. So here we are using an element from the Abacus library, standard library. The geometric order is the order of the shape function. We are using a linear shape function. You can use either a linear or a quadratic shape function. In Abacus, here we are using a linear shape function, and there is something called reduced integration, and the complete details of the element is provided here. C3D8R is the element code. So these element codes you can find in your Abacus documentation. C means continuum element. All brick elements or 3D elements are called continuum elements. C means that. 3D is 3-dimensional element. 8 is the number of nodes in the element. Here we are using a hexahedral element, so there will be 8 nodes here, only at the corner points. So there are 8 nodes, and R means we use reduced integration. Okay. So C means continuum elements. 3D means it's a 3D element. 8 means the number of nodes, and R means we are using reduced integration. For full order integration for 8 noded element, there should be 8 integration points when you do Gauss quadrature. So when you use reduced integration, you'll use number of Gauss quadrature points. Gauss points will be less than 8. Okay. So now, up to now, we have done the pre-processing. After this, we need to solve the job. So in job, you can create a job from your model. So the job file will have all the options consolidated. Whatever options we have given, we have selected till now, it will be consolidated into a set of files. The set of files is called the job file. So let us do a data check. Always do a data check first, because it will tell you whether there are any pre-processing errors. Okay. So the check has been completed. So far there are no errors. So if there is an error, it will throw up. So we have submitted the job and we can monitor it. So it is a linear analysis. So it got over in one iteration. Then you can visualize the results. So this is the visualization module. So here we can see the contours. So on the top right corner, there is something called a frame selector. Here we have selected, we wanted 10 modes. So here every step, every increment gives you the mode shape, one of the mode shapes of your beam. So you can find the frequencies at the bottom here. Here you can find the frequencies. So this is how you do a simple modal simulation. So Abacus, you can get student edition. So that will be available free from the website. You can download it. The one constraint you'll have will be the number of elements that you can use. The mesh size will be a constraint, the number of degrees of freedom that it can handle. So now we'll do a simple transient simulation. So where we are going to give a base excitation to a cantilever beam. and we are going to model a piezoelectric patch. We are going to bond it to the cantilever beam, and we'll see how we can take the voltage out. So we create another part. So 0.2 mm thick PCT patch. So PCT patch will have both elastic properties, which will have its elastic modulus and Poisson's ratio. At the same time, it will have its own electric properties also. So we have to define both. So in property, we'll create another material. So now we'll create this as an orthotropic material. So there will be 3 Young's modulus in 3 different directions. There will be 3 different shear modulus and 3 different Poisson's ratio. So the elastic properties, then here we can assign its electrical permittivity and piezoelectric properties. So here in piezoelectric properties, either it can be the stress coefficient matrix or the strain coefficient matrix. So these values you can get from literature. So I have already made one model because I don't want to shift between windows. So we have assigned the density, the electrical permittivity, the elastic properties for an orthotropic material, and the piezoelectric coefficient, the strain matrix coefficient. So these values you can get from literature. So again we'll assign a section, we'll create a section with the material PCT material we have created, and we'll assign it to this body. So here, since we have defined this material as an orthotropic material, we need to tell the software which will be direction 1, which will be direction 2, and which will be direction 3. Because any material can have a local coordinate system, right? Based on the local coordinate system, only the composite laminates orientations are defined. So here we create the orientation, we define the orientation for this body. So these will be the 1, 2, and 3 directions. Since we did not rotate the body after we created the part, the default orientations are going to match with the orientations of the global coordinate system. So now we'll create another instance of this PCT patch. So we have just placed them relative to each other like this. Spatially, we have just placed them. We have still not bonded them. Now we have to bond them. So for that, there are certain ideal constraints. Here for bonding, rigid bonding, we use something called the tie constraint. So here in interaction, there is something called a create constraint submodule. Here you select the tie constraint, and here we need to select the two surfaces that are to be bonded. So one surface will be your beam surface, the other surface will be the bottom surface of your PCT patch. To access that, you can just hide your beam. So we have tied these two surfaces together, which means we have bonded these two surfaces together. In the constraint terminology, we have tied these two together. Here, tying means you are tying the degrees of freedom of your structure. So every degree of freedom of these two interfaces will take the same values through the simulation, which means they are bonded together, right? So now we'll do a dynamic analysis. We use dynamic implicit. We solve the problem for 0.5 seconds. These are the time step values. So we use an adaptive time step. So the software itself chooses what time step to use to march the problem in. So here we are using a maximum of 100,000 increments, time increments. The initial increment is 0.01 seconds. The minimum increment it can reach is 1 per 1 per minus 10 seconds. So now we define, so now we want to define the base excitation. So here in boundary conditions, initially we constrain all the boundaries. So in the next step, here we need to define a sinusoidal base excitation at the boundary. So what we do is we create something called an amplitude. The amplitude will give you the function in which the base has to be excited with. So here we use periodic. So we will take 10 Hertz, it's circular frequency, it's radian per second. So 10 Hertz will be around 62.8. Simulation starts from time 0. The initial amplitude is 0. So here A and B, see here we can give complex frequencies. So the A denotes the cosine frequencies and B denotes the sine frequencies. So you give 0 here, 1 here. So here we define, so here we select the amplitude, here we define the amplitude is, here amplitude means the function that you are defining. Here this value is the real amplitude, the magnitude of your sine curve. So here we give it 1 mm. So next step, we have a piezoelectric patch. So one of your field variable is the voltage. So how we have defined boundary condition for your displacement degrees of freedom. Similarly, you have to give a boundary condition for your electric potential also. So here in this case, the surface that we have bonded to, there we'll define the potential to be 0. Because we need the potential difference, right? Finally, the difference is what we are going to get. So one surface you set it as 0, the other surface you'll get the potential difference, the difference in potential. So now we'll mesh the part. Just give a data check. Yeah, so now we have submitted the simulation. It will take some time. Before that, we'll see, before the simulation gets over. So these information you will get in any online source. So, but when you are solving a problem, you might need to automate your code. For example, you can use MATLAB as for your optimization toolbox. But how is that toolbox going to access your software backend, not through your graphical user interface, backend, so that you can run your optimization problem or parametric studies, those things you can. So there are different ways to do it. So Abacus itself has a Python interpreter, so you can generate the Python script. So one other way where industries use a lot is using the input file. So when you create a job, so Abacus creates a set of files. So Abacus creates a set of files. Here, the DAT file will contain every information about your job, about your module. It will contain your mesh information, geometry information, the contact information, interface information, boundary conditions, loading conditions, everything will be there. Plus, how your system is handling your job. So, what is the amount of RAM it is taking, what is the clock time it is taking to solve the problem, these information will be there. But the file that will be submitted to your solver is the input file. It has an extension .inp. So the INP file looks like this. So it is a keyword based file. So any line with 2 asterisk symbols is a comment. Any line with just 1 asterisk symbol is a keyword that will be read by your solver. So here we have created a part. Okay, the name of the part is PCT. We have created another part, part 1, which was the beam part. Then we assemble the part. So in assembly we created one instance of the part 1, and it was named part 1-1. Okay, this is the geometry information of the part. These are the coordinates, x, y, z coordinates. Okay, first what we did, we for extrusion we made a flat rectangle, and then we extruded in the z direction. So we just need 2 sets of information. One is the coordinates of the flat rectangle that we created, and the next one is the extruded information. So these are the nodes. So later we discretize the part. So after discretizing, every node will have a coordinate value. So these are the coordinate values, x, y, z coordinate values of every node. So when you write a finite element code in MATLAB, you will define the geometry, you will define the node, and you define something called a connectivity matrix. The connectivity matrix will tell you what are the different nodes which the element connects. This is the nodal information, and this is the element. This gives you the connectivity matrix. For example, element 1 is connected to nodes 34, 35, 46, 45, 1, 2, 13 and 12. This is an 8-noded element, so there are 8 different nodes that are part of this element, and this is the element type which we saw, C3D8R. So here in mesh, I forgot to do something. So here for the PCT patch, we have to assign the element to be piezoelectric. Then only we will get the electric potential as output. Otherwise, it will be just treated as a solid element. So the next step, so here we have assigned, we created a section, a solid section for all the elements in the beam set, which we created as set-beam underscore beam. And there is similarly, there is another instance which is the PCT patch. The geometry information is here, and the nodal information is here. See, there are XYZ values, plus there are 3 other values. This 4 other values. So these values are there because we translated it, we rotated and translated it. Right? This translation information will also be there because your CAD file will have a different origin and your assembly file will have a different origin. So that information will be present here. So there is again the nodal information and the element information. So here we have created a material. The density is provided, Young's modulus is provided. So all the information, whatever we clicked there, will be created here. So if we know how to use or how to create an input file, we don't have to open Abacus. We can just write this file and submit it back in so that it works. So this is how you use it in MATLAB or other softwares. So to do optimization or parametric studies. For example, if you want to change the Young's modulus or the density, here you can change. Here you can change as in the notepad, you can just change the density, save it, and you can submit the file and it will run, okay, with the new values, new set of values. But how will you submit it back in? So what you need to do is, so in your working directory, you you open your command window, and here the command is abacus job, and you give the job name. You give enter and it will start running. So I'll just create a copy of this. You just give enter and it will start running. Everything will start running in the backend. Okay, it will create its own files, input files, output files, data files, message files, everything it will create and it will run. Okay. So this is a longer simulation. So I've already performed the simulation, and to show you how to take the output out from the voltage out from the model is important. So here I go into the visualization module. So E-pot is the electric potential. Okay. So this is so what you need to do is you need to plot the XY data, right? With time, how does your electric potential varies? So what I do is I create an XY data of the field variable of electric potential, and so I just clicked on the node, the particular node where I want to find my electric potential, and I just plot it. So here, the plot looks like this because the values will be saved at the number of time increments that you specify. So here I have specified the time increment to be 0.01 seconds. So at 0 there is no data, it recorded the data. So at 0.01 it recorded the data. It is a base excitation, so it is supposed to be, there should be some transients, and it should also have a sinusoidal voltage output. But here, since I am not recording the data at every time instant I am solving, so I am getting this pattern. So the more data you record, the bigger your files will get. The more output it has to record. So there was some problem in the interface conditions. So one more thing. So how do you decide which output you want from your simulation? So that will be chosen from here. There's something called field output request and history output request. Field output request, you get the output of your field variables, which will be the displacement, strains, stresses, voltage, and everything. So history output will be the time histories. Okay. So what you do is, if you want a specific output, you go create it, and from which step you want to create the output. So here, these are the different outputs you can take out. Stresses, strains, displacements, coordinates. So where is this useful? For example, if you are writing a control problem, because Abacus has its own subroutines, because there is lot of options that are not available in your graphic user interface, but you can write your own Fortran codes and submit it along with your job, and those Fortran codes will have any additional solver that you are writing on your own, right? So these outputs are useful that time. Okay. So all these are written as keywords, and these keywords will be present in your output file. For example, the nodal output taken out from this node set, these are the nodal output you are taking. E pot is the electric potential, U1, U2, U3 are the three displacements, UR is the total, the magnitude of rotation, UR1, UR2, UR3 are the components of the rotation, and UT is the translation. There is any rigid body translation. So you have any questions?
Sir, when you said the PZT is the degree of freedom is constrained with respect to the beam, so that means the elements of both the PZT and the beam should coincide, right? The mesh elements.
Yeah. So that need not be the case. So what it does is it constrains the degrees of freedom that you select, not all the elements. Whatever degrees of freedom that you have selected here, for example, here all the degrees of freedom of the bottom surface of the PCT will be constrained with the degrees of freedom of the portion of the beam on which it is attached. Right. So then only it is called a bonded joint, right? Because they are at the same point. They'll be moving it together in space. They'll be rotating together in space by the same amount. So that is what happens.
So in that patch, and under the lower face of the PZD, the elements will coincide, or it's just
the nodes will coincide.
Nodes will coincide.
From the folder, you have a file called the ODB file. So this is the output database file. So this file is what you select in your visualization model. So this has got all the visualization data. So you can, so if you want to use any open source software, you can use ParaView. ParaView can open ODB files. So this is just a general picture of how it can be used, Abacus can be used. So the key takeaway here will be how to read an input file. Once you understand how to manipulate input files, you can run very fast simulation because you are working with the text documents. So when you are opening a software, it is going to take up a lot of your RAM, and the options that it gives also will be very limited. So when you have your own codes, your own Python codes, your own solvers, but there are certain portions of your code or which needs a complex solver like an Abacus, that time you can use input files. The input files are very useful. So when the systems are very large, for example, you're doing a crash simulation, those even you're loading the software will take a lot of time. Instead, you can just open your text document. You can have your own regex operation in your MATLAB or Python. So where you need to search certain keywords and just change those keywords, certain values you can change, just a find and replace you can do, and you can run a completely new simulation. If you know how to write a mesh, if you can get the mesh data, then the whole mesh data can be written as coordinates and element connectivity matrix as a text file, and you can paste it in your input file. So it gives you a lot of power in automating your simulations. So I'll be present in MSB 104. So if you have any doubts, you can come there.
How to connect the MATLAB program?
So in MATLAB you can write an input file, right? In MATLAB you can create text documents and all that. So I've taught you how to submit the file through your command prompt. From MATLAB you can access your bash or command prompt also. So there is a command called system. In that you can enter all your shell script commands. So by that you can submit your jobs.
But the element size and element connectivity is same. MATLAB.
That you can generate on your own. So either you can mesh it in Abacus. When you mesh in Abacus, you'll get only that information in your input file, And after that, you can add more lines about your solver settings and all that.
Can we make elements and element connectivity in MATLAB then into
Yes,
the
yes, yes. You can do that.
it's possible.
It is possible, but for complex parts, those data get very hard to generate. So you need a mesher. You need a mesh generation tool to get the data. Your
all
simple
type-
parts, you can do it yourself.
All type of optimization is in Abacus.
So Abacus also provide an optimizer, but it is only gradient based optimization. For example, you want to do an optimal sensor placement problem, and you need to shift between the top surface and the bottom surface. So that then gradient based optimization, this is more like a categorical variable, right? You cannot use a gradient based optimization. It is like a plus 1 0. Yeah. Then you need to go for integer programming. Abacus doesn't provide integer programming, but MATLAB does.
Okay, but I have also a question because you select some piezoelectric, but we are using some microfibers composites. So these microfiber composites are not there, only some kind of crystal piezoelectric in this approach. Yeah.
So for that, we can use subroutines, something called UMAT. So we can create our own material in those subroutines, or we can create our own elements that will be appropriate for those kinds of materials. So those options are not provided in MATLAB. We need to write our own subroutines for that.
So the same is also for this electrical, connections. Yeah. So these are not present, and electrodes are not there. Electrodes.
So the thing is, when we do experiments, there'll be two leads that will be coming out, right? So we can take the output over there. But here, in every node, the field variable will be calculated. So we need to do an average of. We need to find the voltage from all the nodes, need to get an average, and then that is what we take out as our output. So these are post processing. So once you solve it, post processing itself will take some time. So you can do the simulation. The Abacus runs the simulation. Only thing we do is the pre-processing part. So this giving proper boundary conditions and all that. Those things are easy. For interpretation, we need to do a set of post-processing. You need to have your own MATLAB code to plot different types of data, because whatever Abacus provides will not be pleasing to us, to the eye. So you take the data out, and then you can write the data out also, and then you do a post-processing MATLAB or Python or anything.